growing threat, please. Because I haven't tell us what the BESS is.
Yes.
Thank you very much. Please introduce yourself.
Okay, hold on. Okay, I'll put my time, so make sure I stick to the time today. So yeah, my name is Maria. I'm from the University of Sheffield. For the last 4 years, I've been doing my PhD together with my supervisors, Dr. Erica Valentine and Professor David Stone. And I've been concentrated on the emissions associated with the energy to charge the fleet. And I would like to present some of the results today here. I've been using solar energy and battery energy storage system, BESS, for fleet charging. And today I'm going to present a case study based on a refuse collection fleet. So the presentation will go through, I will start contextualizing first the research. I will then present the case study and then some results and conclusions. So here in the UK, we generate around 222 billion tons of waste. And the management of this quantity of waste relies on heavy goods vehicles. According to the Department for Transport, heavy goods vehicles represent around 13% of total NOx emissions from road transport in the UK, 19% of greenhouse gas emissions on the total road transport in the UK, while just doing 6% of vehicle miles in the UK. So local authorities are looking into solutions to reduce the greenhouse gas emissions and improve air quality in urban and city areas. One of the things they see as a potential solution is the electrification of fleets, local fleets. The electrification of local fleets not only reduce the greenhouse gas emissions and improve air quality, also diminish the noise provoked by the conventional refuse collection vehicles. But from the point of view of my study, I asked the question, what makes the electrification of refuse collection vehicles a potential solution? So first of all is the well-structured and planned daily routes. That is a benefit when you have to plan the charging of the fleet, because the electrification of the fleet would reduce the noise created by the truck. It opens up the possibility of operating during off-peak hours, and particularly the refuse collection vehicles, because they are on depots, and there is area for rooftop photovoltaic panels, has the potential to charge with localized solar energy. Oops, sorry. So the aim of my study was to assess the impact that different charging patterns have on grid dependency, total cost, greenhouse gas emissions when an electric refuse collection vehicle fleet is charged, considering also the power connection constraint. When the fleet is purely charged from the grid and when the fleet is partly charged with solar energy and energy storage systems. So I made this study based on a local authority waste management depot. It's located in Nottinghamshire in the UK. And they have actually 19 refuse collection vehicles, diesel-powered vehicles. The data we had from them is that the fleet perform 23,000 miles per month. So we have been using a conversion factor to estimate what would be the consumption from the fleet. The number I have considered is 3.5 kilowatt hour per mile. This is between the range on literature, which is around 2.54 more or less. And this number was came from a model one of my colleagues in the University of Sheffield published. So in order to analyze the results, I have been doing three different scenarios. So scenario one assumes that the fleet and the depot would be charged from the grid, 100% dependent from the grid. I have then assumed a second scenario and a third scenario that considers the use of PV panels and battery energy storage system to charge the fleet and the depot, and only use the grid as a second source in case the demand cannot be met by the solar energy. Because I wanted to explore the issue of power connection capacity, I had to add a scenario 3. When the power connection capacity at the depot at the moment is 0.15 megawatts. If they are going to electrify the fleet, the power connection capacity would be 0.6 megawatts. So I am comparing a scenario 1 and a scenario 2, assuming they would upgrade the power connection. And I am comparing a scenario 1 with a scenario 3, assuming they would not upgrade the grid. To assess that, I've been using different charging patterns. So I am considering a day charging patterns in which the 19 electric refuse collection vehicles operates between 6 and 2, and they return to the depot to be charged at 4 p.m. Then I consider a night charging scenario in which the fleet operates between 6 and 2, but they are charged at 9. And then I consider a mixed charging scenario. Part of the fleet will operate between 6 and 10 a.m., then will return to the depot to be charged, and then continue the operation between 6 and 10 p.m. The rest of the fleet would be 9 out of 19 would operate like normal pattern from 6 to 2, and then they would be charged at 11. You see the difference charging times here. For the first two charging patterns, I am considering a 22 kilowatt chargers. And for this pattern, the mix, I am considering 50 kilowatts chargers. In order to get the results, I had to develop an energy management algorithm that controls the energy flows between the system. It controls the energy flow between the panels, the battery energy storage system, the fleet, the depot, and the grid. So you see here a graph that represents monthly energy consumption and generation. The purple color represents energy consumed or purchased from the grid. The yellow one represents the consumption from solar energy. The brown one represents the energy obtained from the battery energy storage system. And then you have light green, which is PV solar surplus generated each month, and then the energy that goes to the battery from the PV panels. And I wanted to put some results here because this scenario considers a battery of 0.5 megawatts hour, whereas this scenario considers a battery of 5 megawatts hour. You can see the capacity of the battery impact the or influence the extent to which the depot relies on the grid. When you use a bigger battery, you see that in summertime, when the solar peaks in the UK, there is a considerable reduction on grid dependency here. So if we look at the results, you can see three different graphs representing the result obtained for the day charging pattern, night charging, and mixed charging pattern. The line represents the percentage of energy covered from the grid. And then you have two pie charts at 0.5 megawatt capacity and 5 megawatt capacity for its charging pattern. The BCS here is the base case scenario that corresponds to a scenario 1, which is 100% dependent from the grid. And then what you can see here is that the use of solar energy and battery energy storage system at different charging patterns reduces the grid dependency. But to what extent the grid dependency is reduced depends on the charging pattern selected. Here, in that case, when we looked at using smaller batteries on site, the mixed charging patterns is the best one because it's the charging pattern that uses the most the instantaneous solar energy. And that's a key point. If we look at total cost, you see here the base case scenario. That scenario, again, is the one that doesn't use solar energy, so it's 100% dependent from the grid. And it has been published before that the best charging scenario corresponds to overnight. Is the scenario that takes advantage of electricity price. So if you are not considering installing solar panels and batteries, overnight charging is the best option in terms of cost. However, installing PV panels on site and battery energy storage system reduces the cost for certain capacities, obviously. And if we look at the best scenario, which corresponds to a mixed charging pattern at 0.5 megawatts hour capacity, the savings could be approximately £1 million over the system lifetime. If we looked at the greenhouse gas emissions, we can present that in two different ways. We can present that as the whole system, like the energy used from the grid, from the solar panels, and so on. And the outputs are very similar, either the charging pattern you use, because the energy consumed is the same, it's just that it's distributed differently. But if we looked at the greenhouse gas emissions from the fleet, is where we see differences and is where we see that the charging patterns affect the greenhouse gas emissions. So as I said before, the more the use of instantaneous solar energy, the better the grid dependency, total cost, and greenhouse gas emissions. As you can see here, the mixed charging pattern, which is this one, is the one that reduces the most the greenhouse gas emissions. Now I wanted to check the power capacity connection, and for that scenario, I only analyzed the night charging pattern. So I wanted to present total cost here, because this is one of the main issues that companies are facing when they decided to electrify the fleet. What happened when we use solar panels and batteries? What are the impacts? So if we looked at a scenario 1, let's assume that the company or the local waste management depot, in that case, they don't want to use solar energy and battery energy storage for different reasons. When they adopt an electric fleet, let's put it that way, the increase on power capacity would be from 0.15 megawatts to 0.6 megawatts. If you don't upgrade the power connection capacity, it could cost around 0.7 million pounds due to the network cost, which has the excess capacity charge on that on that level. So it's always better to upgrade, although it's not always a possibility. When the upgrade is an option, then the use of battery and solar panels is the best to save money. But when there is not an option of upgrade, I wanted to know if the use of solar panel and battery could help with that constraint. And what I found was that, yes, the use of a battery energy storage system and solar energy fulfills the energy requirement because allows the power connection capacity to be below the maximum. So it did not incur in extra charges, as you can see here. But when you consider cost of the battery, you see this is not an economically viable option. So to summarize here, the use of solar energy, and battery energy storage system, yes, reduces total cost, greenhouse gas emissions, and grid dependency when it comes to the electrification of fleets. The extent to what you get more benefits depends on the charging pattern. The logistic companies or the waste management fleet cannot adapt to different operational times. So the charging patterns I assume here doesn't mean that they are feasible or realistic option. I just wanted to provide with broader results, if that makes sense. When we face the power capacity constraint, the use of a battery can fulfill the requirement for the energy, although the cost of the battery is too high and that outweighs the potential benefits of using. So that means it would require not only the use of battery energy storage system, but also other strategies as smart charging or load management to make it economically viable. And that's me. Thank you very much.
Thank you very much, Maria.
Yeah. That was very interesting. I'm not too sure about the photovoltaic and the solar within the detail, but I thought the discussion you have would be very interesting for emerging economies where you really have implications on the grid. There's probably better solar power potential as well. Then what's interesting also that you propose that with the charging transport even reduce the vehicle fleet, you could actually use during the night and charge during the day. Then you would even maybe get rid of some of the batteries you have for the energy storage.
Yes.
In emerging economies, particularly in the UK, I don't know if there's much cloud and rain dark this winter. But I thought that was really interesting for like looking at this application, right? When you have a night operation, maybe